Section: Introduction. In this section, we discuss the challenges posed by the limited context window of early large language models, LLMs, which typically handle around 4,096 tokens. To address this, we utilize retrieval-augmented generation, RAG, to manage larger context corpora. The quality of answers generated by RAG heavily relies on the effectiveness of the retrieval model, prompting us to focus on enhancing retrieval recall and precision. Recently, advanced LLMs have emerged that support much longer context windows, such as GPT-4o and Gemini 1.5 Pro, which can handle up to 1 million tokens. This raises the question of whether RAG is still necessary with these long context models. Our analysis shows that long context LLMs generally provide better answer quality than RAG. We re-evaluate RAG's effectiveness in generating answers with long contexts and find that the order of retrieved chunks significantly impacts answer quality. Unlike traditional RAG, which organizes chunks by relevance, we propose maintaining the original order of chunks from the source text. Our experiments indicate that this order-preserving method enhances answer quality. We also observe that as we increase the number of retrieved chunks, answer quality improves initially but then declines. This happens because while more chunks provide potentially useful information, they can also introduce irrelevant details that confuse the model. Thus, we must balance the amount of relevant information with the risk of distractions to optimize answer quality. Our findings suggest that RAG, when using the order-preserving method, can outperform long-context LLMs that do not use RAG. For instance, in our tests on the NQA dataset, we achieved a score of 44.43 with just 16,000 retrieved tokens using Llama 3.1-70B, while Llama 3.1-70B using the full 128,000 tokens without RAG scored only 34.32. This demonstrates that RAG can yield higher performance even with fewer input tokens. We also explore related work in retrieval-augmented generation, which enhances LLMs by providing up-to-date information and reducing inaccuracies. While long-context LLMs have made RAG less essential, our work shows that the order-preserving RAG can still outperform these models. In our order-preserving RAG approach, we take a long document and divide it into sequential chunks. We then calculate the relevance of each chunk to a given query by measuring the cosine similarity between their embeddings. We retrieve the top chunks based on these scores while maintaining their original order in the document. This method contrasts with traditional RAG, which organizes chunks solely by similarity. Section Summary. In this section, we explore the effectiveness of retrieval-augmented generation, RAG, in the context of long context language models, LLMs, revealing that preserving the original order of retrieved chunks significantly enhances answer quality. Our findings indicate that while increasing the number of retrieved chunks can improve recall, it also risks introducing irrelevant information, highlighting the importance of balancing relevant and distracting content for optimal performance. Section: Experiments. In this section, we conduct experiments using the NQA and NMC datasets from the Infinity Bench benchmark, which is specifically designed for evaluating long context question answering. The NQA dataset includes 351 human annotated question-answer pairs, with an average long context of 150,374 words. We evaluate this dataset using the F1 score. The NMC dataset contains 224 question-answer pairs, also annotated similarly, but each question has 4 answer choices, with an average long context of 142,622 words. We use accuracy as the evaluation metric for NMC. We note that there is another benchmark called Long Bench, but its average context length is under 20,000 words, which is insufficient for assessing recent long context models that support a 128,000 token window size. For our implementation, we set the chunk size to 128 tokens across all datasets, ensuring that the chunks do not overlap. We use the BGE Large NV 1.5 model to extract embeddings for the queries and chunks. In our ablation study, we examine how context length affects the performance of our order preserve RAG. Each chunk contains 128 tokens, making the context length 128 times the number of retrieved chunks. We observe that as the context length increases, performance initially improves because more context can cover relevant chunks. However, beyond a certain point, the quality of answers declines due to the inclusion of irrelevant chunks. Specifically, the Llama 3.1-8b model reaches its peak performance at a context length of 16,000 on both datasets, while the Llama 3.1-70b model peaks at 48,000 on N, QA and 32,000 on N, MC. This suggests that the larger model is better at distinguishing relevant from irrelevant chunks. We also compare our order preserve RAG with the vanilla RAG. When the number of retrieved chunks is small, the advantage of our method is minimal. However, with a larger number of chunks, our order preserve RAG significantly outperforms the vanilla version. For example, on the N, QA dataset, with 128 retrieved chunks, the vanilla RAG achieves an F1 score of 38.40, while our method achieves 44.43. On the N, MC dataset, with 192 chunks, the vanilla RAG scores 81.22 in accuracy, whereas our method scores 88.65. Finally, we compare our order preserve RAG with two types of baseline approaches. The first type uses long context LLMs without RAG, which requires a large number of tokens, making it inefficient and costly. In contrast, our order preserve RAG reduces the token count significantly while improving answer quality. For instance, using the Llama 3.1-70b model, the approach without RAG scores 34.26 F1 with an average of 117,000 tokens, while our op-RAG with 48,000 tokens scores 47.25 F1. The second type of baseline employs the self-route mechanism, which directs queries to either RAG or long context LLM based on self-reflection. Our method outperforms these approaches while using significantly fewer tokens.